Next topic, irrational, rational, and real numbers. So this is section 6.4. Irrational and real numbers. So we're just going to play around with what this means. Ir means not, and then rational. Rational means fraction, so not a fraction. So we're going to look at numbers that can't be written as a fraction. So just a reminder about numbers that can be written as a fraction. Well, any fraction for sure, but decimals aren't obviously fractions unless we read them properly. So 0.25 slang read properly is 2500ths. Right? So decimals are fractions. But sometimes we get these weird decimals like 0.3 repeating, which really means we have threes forever. And we looked at how to convert these repeating decimals into fractions. And so I just want to remind you of that trick here. What we do is we say, okay, let's call the fraction x. X is 0 point, and then write a whole bunch of the repetition. Okay, so that's enough of a bunch. And I'm just going to put my 3 dots to say, yeah, it keeps going like that. Now, since this only has one repeating place, then what I do next is I multiply it by 10. I'm going to write that above. 10x would then equal 3.33333 forever and ever and ever. The trick with doing this now is comparing these two through subtraction. I have 10 of these here and 1 of them there, which in the end leaves me a difference of 9 of those fractions, 9 of those x's. Now up here, notice that pain in the butt forever matches up forever and is going to subtract out. So 3 minus 0 is 3, but then 3/10 minus 3/10 is 0/10. 300ths minus 300ths is 0/100ths. The infinite part is now gone. So I get 9 times my missing fraction is 3. Divide the 9, my missing fraction must be 3/9 or reduced 1/3. Do a different pattern just for fun. Suppose I had 0.02525, like that. So my belief here is that the 25 only repeats, and I just happen to have a 0 sitting right there. So I want to know what this number is. A couple ways to go about doing this, similar to before. Now, what I do is just like before, I say, all right, let's let this number be called x. And I'm going to write it out with a couple of repetitions like that. Now, if I tried to multiply by 10, we saw before that that didn't work out so well. That becomes 0.25252. And notice the repeating parts don't line up, so a subtraction doesn't help. So that right there didn't prove useful. Since this has 2 repeating places, instead of multiplying by 10, multiplying by 100 should be more productive. So then I'm going to say, all right, what is 100 times this number? Well, that's going to shift the decimal point twice, so that should be 2.5252. See if I'm lining stuff up. 5. So I'm just going to erase this part right here so we can better compare. And what I should see now is that some stuff lines up. So in the infinite part, right, that dot, 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 that's a pain, those 5s disappear, the 2 disappear, the 5, the 2. So from the hundreds place onward, if I subtract, things are going to disappear. So I'm just going to rewrite the original number underneath. So the subtraction makes more sense. And then do my subtraction. So 100x minus 1x is 99x's. Over here, I get 2 minus 0 is 2. 5 minus 0 is 5. And then 2 minus 2 is 0. 5 minus 5 is 0. 0, 0, 0, 0, 0, forever and ever and ever. I got rid of the crazy infinity part. Now, I got a slight problem here because when I divide, I don't have a true fraction. This is 2.5 over 99. But I can certainly adjust by multiplying top and bottom by 10 to make it look like a real fraction. So 25 over 990. So whip out your calculator right now, type in 25 over 990, and see if it gives me this decimal I thought it did, with the repeating two fives skipped over one place. So I think 25 divided by 990 should be 0.025252525. Look down. Okay, so what's the point of that? Oops. There we go. That if the decimal terminates, I can tell you what it is as a fraction. If it repeats, I can also tell you what it is as a fraction. And the conclusion we came up to when we were playing with decimals, fractions to decimals, was that a fraction as a decimal either repeats a fixed pattern or terminates. So this is a review of section, I think this was 6.1. Fractions as decimals either terminate or repeat a fixed pattern. And we even went so far as to be able to differentiate based on the fraction, which fractions will terminate and which fractions will repeat. That's a whole nother point, but I'm not going to go over that right now. So if there's a decimal that does not repeat a pattern, it cannot be a fraction. So common examples of this that we're familiar with are pi, 3.14159, blah, blah, blah. It keeps going forever without a fixed pattern. And then the question is, what other numbers are like that? So this number is not a fraction of whole numbers. So I just want to do a few examples of numbers that can't be written as fractions, so there's this whole new class of number that we didn't know about before. And I showed this number, one very much like it, a while ago. So I am making a pattern, but it's not really a fixed repeating pattern, dot, dot, dot. Notice the number of zeros after or in front of each one increases. So first I have 1 0 after the decimal in front of the 1, then 2, then 3, then 4. So I can keep writing this down. I see the pattern, I can write it, but it is not a pattern like this where I have this fixed block that's repeating. This fixed block that's repeating. This is not a fixed block. So it turns out this cannot be written as a fraction. The technical term for fractions of whole numbers, by the way, are rational numbers. So this cannot be written as a rational number. If you ever took like a pre-calculus kind of class, there's a magic number out there called E. Most calculators know E. So if I check with my Desmos calculator, it's got a pi button. An E button, but I bet if I type E, it'll say, yeah, I recognize E. It's 2.718281828, and it looks like there might be a repeating pattern. But if we get a better calculator, let's see, like Google has E. It might show us more decimals. All of a sudden, it breaks down and starts doing other stuff. So it looks like it might be going 1828, 1828, and then all of a sudden it says, nah, never mind, I'm going to do something else now. And as you look out, as you calculate more and more decimal places of E, how you calculate that's a whole nother story beyond the scope of this class. But you find there's no pattern going on there. It just keeps going. They're kind of random, but not really, because this is a very special number. It comes up in mathematics and finance. It comes up in the physics of atomic quantities. It comes up in biology. Just like pi pops up in interesting places, like a circle, E pops up all over the place in just about every area of reality that we have played with so far in our universe. So all of these numbers here that aren't fractions are called irrational numbers. And then there's some special ones like pi and e, and there's a few other ones that have letter names, but most of them don't have special names. Like this number right here is irrational, but it doesn't have a special name. And we could create numbers like this all day long that are irrational. Like the complement of that guy could be something like 0.1, 0.11, 0.1110. So we can just keep playing around making up numbers like this. Where we can see a pattern, but it's not a strictly repeating pattern, which is the same chunk over and over again. The big group of numbers that we have access to as humans that are irrational are roots. And so we'll look at a couple of different kinds of roots. Square root is like the most popular one. There's also cube roots and fourth roots and so on. And so we're going to look at some of these. The simplest root that's irrational is the square root of 2. And so just a reminder about what a root means with a different example. 3 squared is 9. And so we say the square root of 9 is equal to 3. So the square root asks the question, what number can I square to get 9? Question, well, 3 squared equals 9. So that's why 3 is the square root of 9. Now, a slight catch with square roots is that if I take -3 and square it, I also get 9. But when I use this symbol, the answer is 3, not -3. If you wanted -3 to be the answer, your only choice is to put a negative in front of the symbol, and then you get a negative. Ignoring the negative for a second, the square root of 9 is 3, so there's the -3. So most numbers have 2 different square roots. This one right here is referred to as the principal square root. And this one down here, that's the other square root. Doesn't get a special name. So when we use this symbol right here, we mean the non-negative root. All right, so back up to this one here. So this right there means what number squared is equal to 2. And we can try and guess at that number, like I might guess 1, because 1 times 2 is 2. But problem with that is, like I could say, is it 1? 1 squared is 1. So no, it's not 1. Okay, so then I could try, hey, is it 1.5? We could try it. 1.5 squared, whip out the calculator, pretty sure that's 2.25, a little too big. Well, what about 1.4? Now this is getting kind of tedious. Now when I was a kid, they didn't have calculators in the classroom like when I was in high school. And so I would have to like guess and multiply to try and figure this out. So on my paper, I'd scribble 1.4 times 1.4. But now, right, we have these calculators everywhere around us. They're on our phones, they're on our computers. I can just say, hey, what's the square root of 2? And it whips out this number, 1.414213562237. Does it continue? Well, the answer is yeah, it does continue. That was showed a long time ago, but it's not a fraction. So the number I want is close to 1.4. 1.41 is closer, and I can keep getting closer and closer and closer by calculating more spots. How to do that is a whole nother story I don't think we'll get into today. But the point of this is that the square root of 2 is not a rational number. And I'm just going to go over an outline of why it's not rational. So if it was rational, let's suppose it was. So I claim it's not, exclamation point. If it was, question mark, that means the square root of 2 would be equal to a fraction like a over b. Now, usually when we make a fraction, it's reduced. So let's just assume a over b is reduced. Okay. Now, if a over b is the square root of 2, that means if I take that fraction, a over b, and I square it, what should the answer be? Anybody? If I think a over b is the square root and I square it, what will the answer be?
Would it be like 9 square root and then b square root?
That's an A, sorry, not a 9. A, letter A. Nope. So let's look up here. So I think that the square root of 9 is 3. If I square 3, what do I get? 9. So if I square what I think the square root is, I should get back what's inside the box, 2. That's the point of a square root. It's the number that we square to get what's in the box. So we think a over b is the square root. So if we square it, we should get 2 back. Now, cleaning that up a little bit, a over b squared is a squared over b squared. And we think that's equal to 2. We also think a over b is a reduced fraction. Now check this out though. I could take that denominator and multiply it over to the other side. Now, this says a squared is 2 times something. Well, if a number is equal to 2 times something, that means that number is even. So a squared is even. All right, well, a squared is a times a. And if a squared is even, that means a has to be even. Otherwise, how would the 2 get in there? So a is some even number. I squared it, it's still even. Okay, now if a is an even number, that means a is equal to 2 times something. Let's call it 2n. So a squared is equal to 2n squared. And that cleans up a little bit to be 4 times n squared. So taking that back up here, a squared is really 4 times n squared. I got a 2b squared on the other side. I can clean this up a little bit by dividing both sides by 2. If I do that, I get 2n squared equals b squared. Well, what does this tell me about b squared? If b squared is a multiple of 2, what can you tell me about b squared? It is even? Yeah, it's even. All right, so now I know b squared is even, so that means if b squared is even and b squared equals b times b, well, b must be even too. So b is an even number, and a is an even number, but that's a problem because I said a over b was reduced. If a over b is reduced, that means they have no common factors. So I got a problem. How can it be reduced and be even at the same time? So that means my assumption somewhere along the line was wrong. Well, the stuff about even, that's all pretty straightforward. Even's a multiple of 2. So where I must have gone wrong was back here when I said, yeah, let's let it be a fraction. Nope, no can do, not a fraction. You run into this contradiction where you can't find numbers a and b that work. Because if one of them's even, the other has to be even. That means it's not reduced, but I thought it was reduced, and everything goes to hell. So, square root of 2 cannot be written as a fraction, because if we try to make a fraction that works, it's either not exactly 2 when I square it, or it just doesn't exist. Turns out anytime you try to take the square root of a number that's not a perfect square, then you're going to get an irrational number. So you run into a similar problem to this. So square root of a non-perfect square. Is irrational, meaning it can't be a fraction. Now that's only square roots. We have cube roots too. So a cube root is the opposite of a cube. So example of that, if I take 2 and raise it to the third power, that's 2 times 2 times 2, that's 8. So then we have this symbol called cube root. Kind of looks like a square root with a 3 in the hook there. The cube root of 8 must be 2. And so this symbol, the cube root, says what number to the third power equals 8. Well, 2 to the third power is 8. So another example, cube root of 1 is 1, since 1 cubed is 1. Next easiest one, cube root of 27. You might recognize 27 as 3 times 9, and 9 is 3 times 3. So the cube root of 27 must be 3, since 3 cubed is 27. If the number inside isn't a perfect cube, I got a problem. So if I tried to take the cube root of 4, 4 is 2 times 2. It is not a cube. That means this number is also going to be irrational, kind of for a similar reason about the square roots. So when I put it into a calculator, what's going to happen, and there are calculators out there that will give you almost as many decimal places as you ever desire. In a while, it's called Wolfram Alpha. And let's see, another way to write a root, by the way, and we'll test this out, is the power. So the cube root of 8 is also 8 to the power of 1/3. On a computer, I might have to type that as 8 to the power parentheses 1/3. Depends on the calculator. So let's check that before I go into the cube root of 4. So let's just go to a regular calculator. Some calculators have cube root buttons, like this one does. I can say, hey, give me the cube root of 8. Calculator says 2. Or I can say, what is 8 raised to the power? And some of these calculators need parentheses for complicated powers. 1/3. Oops. And calculator says, oh yeah, I recognize 1/3 power as a root. It says the answer is 2. If I tried to take 4, the cube root of 4, let's use the cube root button here, then I'm going to get this decimal, and this decimal goes on for quite a ways without a pattern. So I'm going to use Wolfram Alpha to show me that. So 4 raised to the power 1/3 in parentheses, and Wolfram, let's blow this up a little bit, up front gives me a lot of digits there, and I can keep asking for more digits. Eventually they're going to make me pay for them. And if you scan through this list, what you're going to find is there is no repeating pattern in this list of digits. 1.58740105, blah, 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 blah. It's not like those repeating chunks like 0.33333 or 0.252525. This is a whole other kind of animal, and these animals are called irrational numbers. All right, so we'll play more with irrationals in a second, but I just want to kind of put it all together. If I take all of the rational numbers that exist, right, all those nice fractions, and I combine them with all the irrationals, all the not fractions, together they make this set of numbers called the real numbers. And if anybody ever took a pre-calculus class where you looked at functions, generally those study real numbers, which are rational and irrational. And there's a whole bunch of other subclasses to these. They're what are called polynomial irrational numbers and transcendental irrational numbers. Here I really only care about making a distinction between rational and irrational numbers. And without the irrational numbers, we're missing a lot of reality, depending on your perception of reality. So another example of where this pops up in reality is if I were to draw a triangle. Trying to make those the same length. 1, 2, 3, 4, 5, 6, 7, 8. 8. Yep, they're the same size. And the other thing I'm trying to do is I'm trying to draw a right angle in there. So I want these two perpendicular lines there. And I want them to be the same length. And just for fun, I'm going to call them 1. That's 1 unit long. That's 1 unit long. If I then try and connect their endpoints from here to here, I'm going to get a new line. And the question is, how long is that new line right there? So some of you may remember from your past life in math that when you have a right triangle, there's a thing called the Pythagorean theorem. And I'm going to look at the Pythagorean theorem more carefully in the next course in the geometry section as to why it's true. For now, we're just going to assume it's true. Pythagorean theorem says if you have a right triangle, which I do here, and so I'm just going to draw another one here. The sides aren't necessarily the same length, and there's my right angle. These two sides are usually labeled A and B. They are called the legs of the triangle. They come off of the right angle. This other side's called C. It's also referred to as the hypotenuse. What the Pythagorean theorem says is if you measure the legs, and then you square them, and then you add them up, that's always going to be the same as the square of the measure of the longest side, the hypotenuse. So the sum of the squares of the legs are equal to the square of the hypotenuse. So that's the Pythagorean theorem. So we're just going to apply it to this situation right here. So in this situation, my legs are 1 and 1, and the legs always get squared and added. Okay, we never add the hypotenuse, only add the legs, and it's their squares. That equals the square of the hypotenuse, and I'm saying I don't know what the hypotenuse is. I'm just going to call it a question mark. A lot of times we'll just call it C. Well, let's clean this up a little bit. 1 squared is 1, plus 1 is 2. And so now this says, okay, I need a number whose square is 2. Can anybody tell me what number has a square of 2? 1 squared is 1 and 2 squared is 4, so what number has a square of 2? So we already went over this a few minutes ago. So it would be the square root of 2. Remember, what does the square root tell me? So the square root of 2 means what number squared is 2. And that is exactly what this right here says. This says what number squared is 2. Answer, square root of 2. So I've got this very simple triangle. I've got this nice right angle, and we love right angles in this world for a couple of reasons. I have a very simple triangle with 1 unit there and 1 unit there, And it turns out the distance between the endpoints, that diagonal length in this triangle, is this wild number called the square root of 2, which can't be written as a fraction. So irrational numbers come up in these very simple ways, a very simple triangle. Now, do all triangles have irrational numbers? The answer is no. There's lots of triangles that don't have irrational numbers. And I could make a right triangle. Let's try again. Let's make a right triangle. And I'd like you to try to draw this to the best of your ability. If you have a ruler nearby, that would be even better. So right triangle with legs 3 and 4. So if you have a ruler, draw your best right angle, measure out 3 in one direction, measure out 4 perpendicular to that, and then we want to find the diagonal in between. So I'm going to use my scale here. So let's say here's where I'm going to start, and I'm going to go up 1, 2, 3, 4. So there's my up 4 to the best of my ability, and then from there I want to go over 1, 2, 3. And then I want to know what is the distance diagonal from the endpoints of those 2 segments right there. And I don't have a ruler on the screen, unfortunately. So again, here is my 4, here is my 3, this is a right angle, and I want to know what this missing number is. We'll call it C this time for fun. The fun thing is if you actually measure this out, you can see what it is on the ruler, which is kind of cute. Does anybody have a ruler nearby to try that? If you do, give it a shot. Measure 4 one way, measure 3 the other. This is really cool. Like a lot of schools have these tile floors, right, with these linoleum tiles on the floor, and they're typically 1 foot by 1 foot. And so what you do is you pick a point where the tiles meet, like I did here, and you measure 4 tiles one way, make a mark, 4 tiles the other way, make a mark, and then get out a tape measure or a ruler and measure the distance in between. It's pretty cool. We'll calculate it. So Pythagorean theorem says take the leg 3, square it. Take the other leg 4 and square it. And then we can now solve this to figure out what the missing number is. Let's see, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. So this says what number squared is 25? Square root of 25 is a good day. I think today's a good day. 5, yeah, it is 5. So it turns out if you built this thing and you had a good right angle and you had a good measure for 3 and a good measure for 4, your tape measure or your ruler should show you that's pretty damn close to 5. If it's not exactly 5, that means we have some error. Either our angle's not right, or that's not 4, or that's not 3, or all 3 are messed up. So this is something I use in construction projects sometimes. I have a square in, when I do construction, but squares are typically like 8 inches by 12 inches, or maybe they're 2 feet by 1.5 feet. But maybe I have this wall that's 10 feet tall, and I want to make sure it hits square to the floor. And so what I could do is just on that wall, I measure up. Oh, it's not up very good. I would measure up on that wall, find 4 feet, and then I would measure out on the floor, perpendicular to the wall, find my 3-foot mark, which probably would be like over here, and then I would double check, does the 4-foot point, cannot draw lines today, does the 4-foot point meet the 3-foot point at a 5-foot distance? If they do match up, that means this angle is a right angle. If they don't, that means something's wrong. Either the angle's not right, or the 3-foot's not right, or the 4-foot's not right. But this is a nice triangle. It's called a 3, 4, 5 triangle. Since the numbers 3, 4, and 5 are whole numbers, those 3 numbers are referred to as a Pythagorean triple. And there's infinitely many different Pythagorean triples out there. There's a whole bunch of proportional ones. Like I could double all of those. So double 3 and I get 6, double 4 and I get 8, double 5 and I get 10. But that's not really a new Pythagorean triple because I just doubled those. So there's infinitely many more Pythagorean triples that aren't proportional to a 3, 4, 5 triangle. Anyway, so that's what we're going to play with next. We're just going to make some irrational numbers by building triangles. And when we build triangles, we can only measure a diagonal from a right triangle is the way we're going to go about this. So we're going to play around with the next activity. Just double check. Over all the main ideas. Yes. Okay, so these are all the main ideas in section, or most of them. In section 6.4, let's go home here. I'll get to Adley's question in a few minutes, but first I want to play around with this activity, measurements that aren't rational.